In this video, we'll show how to solve the following question. Find all solutions, w, x, y, z, in real numbers to the system of linear equations given over here. So these are three equations in four variables, w, x, y, z. So it turns out we'll have infinitely many solutions. There won't be only one. And we'll find all of them. Okay, so the solution is, we'll first form the augmented matrix. That's so we don't have to keep writing w, x, y, z all the time. The augmented matrix, again, is so we take this first equation here, and that forms the first row. 2, 3, 4, negative 1, 2, 3, 4, negative 1. And then this vertical sign here stands for the equal sign. And so then we have the 1, 2, 4 on the right of this. This is what the augmented refers to. It's this extra column out here. Sometimes I'll drop writing this vertical line. Okay, now this second equation, now there's equally a 0w here. So that's where this 0 comes from. You have to match up the variables correctly. So the w's are all start here, the x's start here, the y's are listed here, and the z's are listed here. So you have to be consistent that way. Okay, so and then this x is a 1x, so that's where there's this 1 here. Likewise for y and z, so we've got 1, 1, 1, and then this 2 comes from that 2. Similarly, for the third equation, we've got 2, 0x, 2, 2, 4. So we've got 2, 0, 2, 2, 4. Okay, great. Now, our goal is to get the matrix in a form called reduced row echelon form. I won't give the precise definition right now, but the idea is we're going to have a bunch of 1s, and beneath the 1s and above it, in each column, are 0s. We'll use these 1s called pivot 1s to make a bunch of 0s below it and above it to clear out. And then once we've done that, we can easily read off the solution. That's sort of the whole point of getting all these 1s is, for example, this equation here will turn into, let's see, w, x, y. Y plus some number times z equals some number, and we'll be able to solve for y. Okay. So what can we do? Well, we're allowed to use just 3 simple steps or procedures repeatedly. So the first one, again, this is just my own labeling. You can scale a row. In other words, multiply through any row, both on the left side of the vertical line and on the right, by a number that's non-zero. Interchange 2 rows, and then the third one is replace a row by adding to it a multiple of another row. Okay, so one thing I should say is that there's multiple ways to get started, and at each step there's multiple things you could do, and eventually the final answer will be the same regardless of what steps you chose. Okay, so what I decided to do, again, here's our matrix. Here's our matrix out here, and I'm trying to get a 1 out there. Now, there's a few things I could do. Here's the one thing I didn't do, but what I could have done. I could take this row, and I usually say divide through by 2. Technically, it's multiply by 1/2, multiply through by 1/2, but let me go ahead and just say divide this entire row by 2. That would definitely give me a 1, and this would become 3/2, which is fine. Fractions are allowed, and so forth. But because I don't like working with fractions and I'm doing this by hand, I decided not to do that, but it is a step I could do. So let me tell you what I did instead. So I took this third row and divided that through by by positive 2. And then I get a 1 here. That's why I did that. So I get a 1. So then I get 1, 0, these 2, 2, and 4. When I half each of them, they turn into 1, 1, and 2. Okay, so now I've highlighted in green here this pivot 1. I'm really looking for the 1 here in the first column. And that's going to help me then clear out everything else. So I move it to the top spot by using the interchange operation. So I'm going to interchange the third row and the first row. So that's what I've done here. Next, I want to turn this 2 into a 0. I mean, fortunately, this is already a 0, but I need to turn this 2 into 0. That way, I'll have zeros beneath this 1. And so to do that, I'm going to replace this row by adding to it -2 times the first row. So -2 times row 1 is computed here. I've taken 1 times -2 is -2, 0 times -2 is 0, 1 times -2 is -2, and so on. Then I've copied over the third row, and then now I've done the addition. -2 and 2 is 0. That's the key point. And then the others, I just do the arithmetic there. And then I replace the third row by that. Okay, so let me just repeat this E3 operation. It's replace this row by adding to it -2 times the first row. And so then I have a 0 here. And so then we're done with this column because we've got a 1 and zeros beneath it. Next, we move on to the second column. Here I've just copied it over from the previous slide. Okay, so we want to turn this 3 into a 0. We have this pivot 1 conveniently for us. And so what we do is replace this row by adding to it -3 times row 2. So here I've copied over the third row. I'm going to add to that -3 times row 2. 0 times -3 is 0. 1 times -3 is -3. These two numbers also become -3. And 2 times -3 is 6. Then I do the arithmetic. And again, the key point is that the -3 and 3, this 3 here, is going to turn into a 0. So then when I replace my original row 3 with the new row is this. Okay, now at this step, what I could do is multiply through by -1, and that would give me a pivot 1 here. But what I did before doing that is just replace, so here, what I want to do next is turn this 1 and this 1 into a 0, because I've got essentially a pivot 1. I mean, it's a -1, but that's basically close enough. So I got a 0 here by replacing this row by adding to it the third row. And then I also turned this 1 into a 0 by adding to it the third row. So that's what we have here. It's just a coincidence that the 0, -5, -7 is the same exact thing as 0, -5, -7 here. But okay. And then finally, I switch this -1 to a +1 by multiplying through by -1. So the -6 turned into +6, ditto with 9, or -9. Now the matrix is in reduced row echelon form. I haven't formally defined that yet, but the main idea is you've got each column, well, the first column begins with the 1, zeros below it. The next column, the very first 1 going down, is after the 1 in the previous row, and then zeros elsewhere in the column, and then repeated like that. Okay, and then when we can just easily read off the solution from this. The first row, when we translate it to an equation, it says 1 times w plus 0 times x, so I didn't bother writing that, plus 0 times y minus 5 times z is equal to -7. That's, again, how we went from matrices to equations. This matrix is short form, or shorthand, for this pair, the triple of equations. Similarly, the second row is 0w, so I didn't bother writing that, plus 1x, plus 0y, so I didn't bother writing that, and -5z is equal to -7. And finally, the third row is, again, 0w, 0x, y plus 6z is equal to 9. Okay, here I've just copied the last few lines up here. And now what we can do is solve for w by adding to the first equation 5z to both sides, or another way of saying is moving the 5z over. So we get that w equals -7 plus 5z. X then similarly is -7 plus 5z. Again, I've moved the 5z over by adding it to both sides, so that's why there's a plus 5z here. And then similarly, y is equal to 9 minus 6z. And then there's no equation for z. Z is just z. And so z is what's called a free variable. It can be anything. And then all the solutions, w, x, y, z, are given by this answer above. So we found, this is the answer that I've boxed. What does it mean? Well, if you want specific numbers, let's take z equals 0. And when z is equal to 0, that means w is, well, all these things involving z are 0. So w is just -7, x is -7, y is 9, and z is 0. So that gives rise to this quadruple of w, x, y, z. This notation means w is -7, x is -7, y is 9, and z is 0. That's because the variables are written like so. Okay, and another choice of z, like z could be 2, or it could be 1, or it could be 1/2, but whatever. So if z is equal to 2, for example, then, well, here's z equals 2. W is going to be -7 plus 5 times 2. 5 times 2 is 10. -7 plus 10 is 3. So that's how I get this 3 here, and then you can trust me on the other two variables or numbers. Okay, so this is how to solve the system of equations using the elementary row operations. This procedure is called Gauss-Jordan elimination or Gaussian elimination. Now, it's very easy to make small arithmetic errors when doing this process, and so therefore it's good to check in Sage that you've done this correctly. So here's the code to enter in Sage. So first of all, we need to enter our matrix. So I chose a matrix variable like A, and then I use the command matrix. QQ is for the rational numbers. That's where these entries all lie. And they also lie in the integers, but it's better for various reasons because we're going to be multiplying through by 1/2 and so forth, that we want to work in the rational numbers. Then we enter a 3×5 matrix. So that's what these two numbers mean next. The 3 is always the number of rows. And the first number is always the number of rows. The second number is always the number of columns. So in this case, there's 5 columns if we include the augmented column. And okay, and then in one fell swoop, you just enter the numbers in the matrix row-wise. So 2, 3, 4, -1, 1, and then I just keep continuing on to the next row, 0, 1, so 0, 1, 1, 1, 1, and so forth. And that will store A as this matrix, and then if you ask Sage what is A, well, it'll give you back this. And then what is the reduced row echelon form of A? To find that out, you do A dot RRF parentheses, and it gives this, and this is the answer we found for that matrix. It had 1s along the diagonal, and then 6, 9, and -5, -7.